on Tuesday when I explained this stuff, I'm motivated by the geometric aspects of directional derivatives and graphs and tangent planes and tangent lines. So now I want to start with sort of slightly different end, which is one of the applications of this technique. In other words, what is a real life situation where we might be interested in finding directional derivatives? And I explained last time the directional derivative is just a fancy term for the rate of change. And so here's a typical example, which you may have already seen in the book or in your section work, which is imagine a mountain, okay? And then there is the ocean somewhere next to it, the beach. But we'll talk about this later. Focus on the mountain for now. Okay, this is a mountain. Now, if I draw it like this, it's not clear whether it is a mountain or just a curve, right? So in order to give it an illusion of 3D, of three-dimensional picture, what I usually do as a reflex, and what you would normally do, or when you read the book, what you see there, is that you draw some curves on it. You're kind of trying to give it a three-dimensional feel, right? So my first point is, what are these curves? These are the level curves. So that's the first thing I want to say, which of course is I've said it before, but I just want to emphasize it one more time. Even to visualize this three-dimensional object on the plane, we find it very convenient, very useful to imagine not just the contour, the general contour of this object, but this collection of curves, which are kind of parallel to each other. What are they? Were they just obtained by taking the section of the mountain by parallel planes, by parallel horizontal planes, which are parallel to the floor, to the ground. Okay, that's what they are. Well, in fact, I have drawn just the visible parts of those curves. Right? There is also a backside for each curve. For example, this one also has a backside. We don't see it unless it's a transparent object. We don't see it. So that's why I usually indicate like this. Right? So each of them has a sort of a second half, which is behind, which you don't see. And this we also don't see when we look at the actual mountain. But when we try to draw the picture, then we draw this. Okay, so that's the first point. So the second point is what does it have to do with directional derivatives? The directional derivative is the rate of change. So change of what? So in this particular setting, there's a very good example of this, which is that suppose that there is somebody here on this mountain who is climbing it. Okay, so there's a climber, and so the climber wants to decide which way they should go to, and depending on which way they go, what will be the rate of the how steep will the climb be? That's the question. So the rate of change will be here the rate of its altitude change, or his or her altitude change, right? And the higher the rate, the steeper is the climb in case we are going towards the top of the mountain, or the steeper the descent if we're going down. And likewise, the smaller the rate of change, the smaller is the steepness. So how do we measure this? The point is that there isn't a single number. There isn't a single number to give us the steepness of the climb, because the climber could go in many different directions, and for each direction there's a particular steepness rate. For instance, the climber may be tired and doesn't want to climb anymore. So in that case, the climber could just go along the level curve. So then the altitude of the climber, the height of this point over the sea level, will not change at all. So then the rate of change or the steepness level is zero. Steepness rate is zero, right? So that's one possibility. That would correspond to going in this direction. But on the other hand, the climber could choose the steepest path, which would actually be, if you think about it, just intuitively, you can guess that it should be something which is perpendicular to the level curve. And in fact, this is something that we have confirmed by calculation, and I will go over it one more time in a couple minutes. So in that case, the rate of change is the highest possible. So in this direction, the rate of change is zero. In this direction, the rate of change is maximal. And if we go in a direction which is perpendicular to the level curve, but we go down, then it's going to be minimal, the smallest possible. Well, its absolute value is still going to be the highest possible, but it's going to have a negative sign. So as a number, it will be the smallest possible value. So here, the rate is minimal. Okay, and so so in order to talk about the rate of change, you have to choose a direction. That's why it's a directional derivative. There isn't a single derivative for a function of two variables, but there's a whole variety of derivatives. A derivative is determined by the choice of the direction. Okay, so what are the variables here? Which variables am I talking about? Well, the variables are somewhere here. So there is let's actually do it. Let's do it on this board, because I don't want to mess up the picture. So I want to draw the coordinate system, and let's say this plateau, this plane, xy plane, is the sea level, and the z then will correspond to the height, the altitude above the sea level. Now our point has a projection onto the plane, and so on the plane it has coordinates x and y, or maybe x0, y0, to emphasize that these are some fixed numbers. So these are the coordinates this corresponds to the position of the climber. You see, the point is the climber is in space, right? So a priori the climber has three coordinates, x, y, and z. But because the climber is not flying, he's not jumping with a parachute, he is on the mountain. Because he's on the mountain, as soon as we know the x, y coordinates, we know the z coordinate, unless the mountain has a shape which sort of comes back, right? But normally, for normal mountain, it's not going to happen, right? So then the z coordinate is actually determined by the x, y coordinates. That's why the only parameters here are x and y, and not x, y, and z. In fact, you can think of the surface as a graph of a function. Graph represents the mountain. Okay, and so now when we talk about the direction, we can think about the direction as being the direction on the mountain, but we can also think about the direction as being the direction on the xy plane. And so, in other words, what we can do is we can drop the level curve down here, and it's not going to look exactly the same because I kind of magnified the picture compared to the picture here. This is big. I have used a different scale for the bottom picture as opposed to the top picture. So the level curve will look like an ellipse, but I have magnified it. I have rescaled it to make it bigger so that it's easier to draw. So then the directions which we have talked about here are the following. This one goes parallel to the level curve. that's the direction along the xy plane or in the xy plane, which will correspond to the movement on the mountain parallel to the level curve. This is the direction on the xy plane, which will correspond to to the path of steepest descent, for which the rate is maximal. And this will be the direction for which the rate will be minimal. So this is what we call the rate of steepest descent. Now, I would like to draw these vectors actually to be in such a way that they are of the same length, because they're supposed to be unit vectors. This is a convention. We agree from the beginning that we will measure directions by unit vectors. Okay. And the point is that these are perpendicular. So what are these vectors? This again is a vector parallel to the level curve, and this vector is a vector perpendicular to the level curve. And this is what we discussed last time. I mean, both of these vectors are perpendicular to the level curve, and the one which corresponds to the steepest descent is the one which is the gradient vector. So this is actually the gradient vector. So this is not left. Because this to get the steepest ascent, you have to go inside this level curve, right? Because you go towards the center of the mountain, and this one will be negative. Will be negative. And the point is that I explained last time why this gradient vector is actually perpendicular to the tangent vector, or in other words, perpendicular to the tangent line, to the level curve. This is some calculation which involved the knowledge of equations for lines on the plane. Okay, so that's the picture. But in principle, there are many other directions we can also draw. We can also draw a direction like this, say, again some unit vector u, which would be AB, which will have two coordinates A and B. And if the climber goes in this direction, then her path would go along that, and it will correspond to some path on the mountain, like this, which is neither the steepest descent nor the steepest descent, nor is it parallel to the slope. You see, in this case, it goes down because the vector points outward. So this direction, or more precisely, this line, which contains this vector, will correspond on the mountain to some specific path, which starts at this point and then goes somewhere. Okay, and what we are calculating is just the slope of that curve, of that path. So the directional derivative d sub u f x0 y0 with respect to this vector u is the slope of the path on the mountain or on the graph corresponding to the line containing u. You see, this is the line I'm talking about, this yellow line. Well, I didn't draw it very well. Maybe it more goes like this. So if I look at this line will give me that path. What do I mean by give me? If I lift that path, there's a path on the plane, on the xy plane, but it has a unique lift to the graph. This is the yellow path on the graph. In other words, this line, or this half line, is the projection of that path. There's a unique path on the mountain which starts at that point, and whose projection onto the xy plane is the half line directed by u. You see what I mean? Are there any questions about this? Okay. So the point is that the graph is two-dimensional. It's a surface. But once you choose a direction, you cut a path or a curve on that surface. So you're back to the one-dimensional case. And in the one-dimensional case, you can actually talk about the slope, because you get the graph of a function one variable, namely the variable along this line, and you can talk about its slope. That slope is the rate of change along that path. That's what we call the directional derivative. And finally, we have a formula for it, which involves the gradient vector, And this formula tells us when this directional derivative takes some particular values. For example, the maximum value corresponds to u equal nabla. Minimum value is its opposite. And the zero value corresponds to the tangent, to the u, which is tangent to level curve. Okay, but this we already knew by analyzing this picture just on the grounds of common sense. We didn't need to do any calculation to figure this out. In fact, when you are climbing the mountain, you are not pulling out a paper pad and a pen and starting to calculate what is the best way to reach the top of the mountain. You kind of follow your intuition, and what your intuition will always tell you is that if you want to reach the top in the fastest possible way, you have to go perpendicular to the level curve, in the direction perpendicular to the level curve. And likewise, if you want to go down the fastest way, you also go perpendicular to the level curve. Is that clear? Okay, so intuitively it's clear, but now we have proved it because we found the formula for the rate of change, and from this formula, written in terms of dot product, it's plain obvious when it takes the maximum value, the minimum value, or the zero value. And that was one of the main conclusions last time, but now I have illustrated it in this way. Okay. So now, one more. Oh, that's odd. There's a problem. That's called catch-22. All right. So I have just a small inconvenience. All right, that's very clever. I will not try to get it out of there because I don't want to put the second one. So yes. What is that? What is that symbol? It's called nabla. It's a Greek letter, which is written opposite to delta. But I'm using it for the gradient. I'm sorry? That's right. This is a notation for the gradient. Okay. So, and one other thing which I wanted to mention in this regard is we talked about equations of tangent lines and tangent planes. And I know that this could be confusing because you have many different objects at the same time for which you can look at tangent lines and tangent planes. seems like there are many different discussions going on at the same time. Okay, let's focus. Okay, so the tangent lines and tangent planes. And so I just wanted to summarize the stuff once more so that there's no ambiguity, there's no confusion. So the first is a two-variable case. In two-variable case, we look at the level curve of a function f of xy. So it is given by this equation, xy equals k. So that's this level curve, that's this curve of equal height or equal altitude, which I do over there. Okay, and so then we can look at the tangent line to this curve. And the equation of this tangent line at the point x0, y0 is like this. It's f sub x at x0, y0 times x minus x0 plus f sub y, 0, y0 times y minus y0 equals 0. Okay? But in fact, we can now look at the case of three variables as well. Right? So let me do it here. Three variable case. In three-variable case, we would want to take, instead of a function in two variables, f of xy, we would want to take a function, maybe f capital, a function in three variables, x, y, z. And by analogy, we would have to look at the level, but not curve, now level surface. The level surface of this function. And so that would be f of x, y, z equals k. Maybe I should say the k is some number. K is a number. So that's, for example, in this discussion, k would be the height. So I don't know, 1,000 feet. Whereas x and y and z are variables. So that's the difference. It's an equation. It's one equation for three variables. Because in this equation, this is some number, like 1,000. So then you can ask, what is the equation of the tangent, but now not line, but plane, to the surface at the point x0, y0, and z0. And you see, the point is that the answer is given by something which looks exactly the same, except now we have three variables. So we have to add one more term, which involves the third variable z. So what the answer is the following. You have to take the partial derivative with respect to x, multiplied by x minus x0, plus the partial derivative with respect to y, plus the partial derivative with respect to z now, also. So the difference between the two-variable case and the three-variable case is that we now have an extra variable. So everything gets dimension one higher, gets bumped by one. We had a curve, now we have surface, we had a line, now we have a plane. The equation here involves two partial derivatives and had this very simple form, and now the equation involves all three partial derivatives but has the same form. Okay? So I will not derive this formula. It is derived in the same way as in this case, in the case of two variables. But I hope it was convincing to you because you can clearly see the analogy. And in fact, if you want to prove it, you can prove it in exactly the same way. Now, what is slightly confusing in this is because there is a special case of this three-variable picture. And the special case is when f of x, y, z is f of xy minus z. So you can ask, why would we even bother to look at this special case? And the reason is very simple, because in this special case, if I look at the equation f of x, y, z equals 0, which is a special case of a level surface, namely the case when k is 0, right? This is just the equation z equals f of xy. And this equation defines a graph of a function in two variables. So it's kind of funny that function in two variables shows up in two different contexts. It shows up here in the context of level curves, okay? But it also can show up here for functions in three variables, even though it is a function of two variables. But even when we have a function in two variables and we think about graphs, we automatically go to the three-dimensional situation, right? And so the graph of a function in two variables can be thought of as a level surface for a function in three variables. Which function? Well, this function, f of xy minus z. It's kind of the simplest concoction you can make out of f and the new variable z. So we can apply this general formula for the tangent plane to this special case, and what do we get? Let's observe that f sub x is just f small sub x, because when you take partial derivative of this function v f, you have to differentiate this one, that would be just f sub x, and you differentiate this one, but this one is independent of x. So this doesn't change anything. So the partial derivative of this whole function with respect to x is just a partial derivative of this part, so this small f sub x. Partial derivative with respect to y is f sub y. Partial derivative with respect to z is what? Negative 1. It's negative 1 because that's the derivative of this function, negative z, with respect to z. This guy doesn't depend on z, so its partial derivative with respect to z is 0, but the partial derivative of this term is negative 1. So we get this three partial derivatives, which we substitute into this formula, and what do we get? We get f sub x of x0, y0 times x minus x0 plus f sub x 0, y0, y minus y0 minus z z0, okay, equals 0. And now we recognize the equation of the tangent plane to the graph, which we have known already. This is the one which we got already 2 weeks ago when we talked about differentials and linear approximation. The only difference is that now I put negative z minus z0 on the left-hand side, but in our old discussion we would write equals z minus z0.